Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of the data structures lectures, we have discussed a lot about the synchronization problems. We have seen that the synchronization problems require the four conditions to be satisfied. In fact, the solution to the synchronization problem requires four conditions to be satisfied, known as the mutual exclusion, bounded weight, progress property and architectural neutrality. With the help of the semaphores, we have seen that this can be achieved, or all these four conditions can be achieved. But if we allow the preemptions to take place in between, and we allow the order of the P and the V operations, or the weight and the signal operations in the correct way, the system cannot enter into the deadlock. For understanding the deadlock, it is a bottleneck like situation, and we will see with the help of the examples that how the deadlock can be characterized in the operating system. So, the outline of the lecture would be that we will first discuss about the deadlock basics, then we will see that what are the necessary conditions for the deadlock, we will see that how can the deadlock be characterized, and what are the different methods to handle the deadlocks, and finally, we will discuss about the deadlock prevention. Check this diagram. This diagram says that this is a diagram of some four-way crossing. In this four-way crossing, the cars are coming from the different ways. For example, these cars are coming to this direction and they want to go in this direction. These cars are coming from this direction and want to go in this direction. These cars are coming from this direction and they wish to go in this direction. Similarly, these cars are coming in this direction and they wish to go in this direction, but none of them can move. It is a bottleneck like situation. At the four-way crossing, the situation is like no car can move. Similarly, in this diagram, this is the example wherein there are four four-way crossings here, here, here and here. The traffic coming from this side wishes to go here, the traffic coming from this side wishes to go here, and the traffic coming from this side wants to go there. Similarly, traffic coming from this side wants to go there, but none can move. This is actually the condition of the bottleneck, and bottleneck is the deadlock. Every situation of the bottleneck is actually the deadlock. We are landed up in some situation where we have no solution whatsoever. We want the traffic to move, but the traffic cannot move, there is no way the traffic can move. So, this is the bottleneck or the deadlock situation. The similar situation arises in the case of the computer system as well, when we are running multiple processes. When multiple processes are trying to access to the common resources and they fall in the circular weight, this actually becomes the condition of the deadlock. But there are two different things. One is the deadlock that we denote like this, and other one is the starvation. There is a slight difference between the deadlock and the starvation. For example, we are dealing with, let us say, the priority scheduling. When we are dealing with the priority scheduling and we have to execute a low priority process, the low priority process cannot be allowed the execution at the CPU when the high priority process is already running, and the high priority process keep coming, then the low priority process will not be allowed to enter for executing the critical section or for executing the CPU. Now, what is happening here, that the low priority process is in the starvation stage, it is not in the deadlock stage. Let us say the moment the high priority process end up, the low priority process can certainly be given the CPU. So, it is a condition of the starvation. A process has to wait for a longer time, but not indefinitely. But in the case of the deadlock, the processes will have to keep indefinitely. So, the indefinite wait is a deadlock, but the definite wait, or you can say that you are sure that whenever the system improves, this resource will be granted to a process. So, that situation will be known as the starvation. So, we have differentiated between the deadlock and the starvation condition. To understand the deadlock, let us establish some model and let us deal it with the help of the diagrams, and then only we will be able to understand the actual deadlocks that takes place in the operating system. So, let us say we have some resources in the system numbered as R1, R2 and so on so forth Rm. So, there are m resource types, Please make it sure that you understand the resource types, not the resources. Let us say there are 7 printers. So, we will actually categorize it, let us say Rp. So, Rp is representing the printer, and if we will talk about the number of the printers, then we will say that this is 7. We will not say that this is R1, R2, R3 and so on so forth R7. We will not say this, saying this will be wrong. We have a printer that has a count 7. So, a Ri resource has xi instances. For example, here the Rp resource has 7 instances. There are 7 printers. Okay. Whenever a process has to use the resources, or whenever the process will demand for the resources, the following functions will be used: the request for accessing to the resource, then use, if the resource is granted to the process can use it, and finally, when the process is done with those resources, it will release those resources. So, there are 3 functions that you should also always remember: request, use and release. Now, these are the 4 conditions for the deadlock. If all these 4 conditions are satisfied, then only in the system there will be deadlock. Okay. So, the first condition is mutual exclusion. Mutual exclusion condition says that we are dealing with a system wherein resource sharing is not allowed. It means, if there is a resource that cannot be shared among 2 processes at the same time. If one process is using that resource, the second one cannot use that. So, we are dealing with the dedicated resources. The example of the dedicated resource in our computer system could be the keyboard. A keyboard is a resource which is the dedicated resource. Similarly, the mouse is also a resource, that is the keyboard, that is the dedicated resource. Similarly, the printer is a dedicated resource. If there is single printer, then we will say that that is a dedicated resource. Only one process can print in that system. But there are several resources which are shared among various processes. For example, main memory, we can accommodate thousands of the processes in the main memory. Similarly, the CPU, if there are multi cores, then we can say that multiple processes can execute in the CPU at the same time. But if you have only single core, CPU will be dedicated resource. So, if this is CPU is the single core system, we will say that that is the dedicated resource. Similarly, the hard disk is a shared resource where several processes can reside at the same time, or several files can reside at the same time. Okay. So, these are the shared resources. For example, a monitor. So, you can show the output of various programs at the same time on the monitor. So, the display device or the monitor has become the shared resource. So, when we are dealing with the deadlock or conditions for the deadlock, let us make it sure that we are actually going with the dedicated resources, and the dedicated resources cannot be used by the multiple processes at the same time. Now, the second condition is the hold and wait. Hold and wait says that a process has acquired some resources and it is demanding for more. For example, a PI process is there, and PI process has already the access to the resources, let us say R1, R6 and R8. So, this already is accessing these resources, the PI process, and it is demanding for more resources. Let us say it is demanding for the resources, let us say R4, R3 and R2. So, while holding some resources, the PI process is requesting for more resources. So, this condition is hold and wait. So, whenever this condition will be there, a system may be there in the deadlock. No preemption means the resources are already allocated to the process. Let us say I cannot fulfill the demand of a process. If we take this example only, in which we have the process R1, R2 and R8 which are allocated to the process, and it is demanding for the resource R4, R3 and R2. Let us say we cannot allocate the R4, R3 and R2 to the process number PI. So, we are not able to give the processes resources to the process, then also the preemptions cannot take place. Preemption means these resources means R1, R6 and R8 which are allocated to PI process cannot be taken back. So, if the preemptions are not allowed, we say that this system may be there in the deadlock. And finally, the cyclic wait. The meaning of the cyclic wait would be, let us see with the example. Let us say there is a P1 process, and the P1 process is requesting for a resource, and that resource is given to P2 process. That resource is allocated to P2 process, and then let us say P2 process is requesting for a resource which is held by or which is taken by, let us say, some P3 process. Similarly, let us say this P3 process is requesting for a resource which is currently being held by, let us say, P1 process. So, P1 is requesting for a resource held by P2, P2 is requesting for a resource held by P3, and P3 is requesting for a resource held by P1. So, they are in the cyclic wait. This condition is called the cyclic wait. They are in the cycle. ना तो P1 प्रोसेस अपने रिसोर्स को छोड़ेगा, ना P2 को मिलेगा, ना तो P2 प्रोसेस अपने रिसोर्स को छोड़ेगा, ना P1 को मिलेगा, ना तो P3 अपने रिसोर्स को छोड़ेगा, ना P2 को मिलेगा, ना ही P3 अपने रिसोर्स को छोड़ेगा, ना P1 को मिलेगा. So they are in the cyclic wait. So they are in the indefinite wait. A cyclic wait has arisen. So if the cyclic wait is there, our system can fall into the deadlock. Now here it is said that my system may be there in the deadlock, my system may not be there in the deadlock. If all these four conditions are satisfied at the same time, we will say that my system is there in the deadlock definitely. If any of these four conditions are not satisfied, then we cannot confidently say that the system is in the deadlock. System may be there in the deadlock, system may not be there in the deadlock. Okay? So to characterize this, or to know that when to say that there is a deadlock in the system and when not to say that the system is in the deadlock, let us check this question, and then we will see with the help of the example that how can we say that the system is definitely in the deadlock and why not, and in which condition we will say the system is not in the deadlock. So now let's take this one. So here we are taking use of the semaphores and the functions for the semaphore named as P and V. What were the P and the V? P is the wait operation and V is the signal operation. The wait operation checks for the entry into the critical section. It checks the value of the semaphore. If the value of the semaphore is your desirable one, you can enter in the critical section. If it is not desirable, you cannot enter in the critical section. Usually what happens that when a process checks that the value of the semaphore is positive, it can enter into the critical section. If the value is not positive, it is 0 or negative, it cannot enter into the critical section. Fine. So here we are dealing with let us say the A and the B semaphore, the value of the A and B is initialized to 1, hence we are dealing with the binary semaphore. Here it is being asked that whether the mutual exclusion is guaranteed or not. So let us check it with the statements. Let us number the statement 1, 2, 3 and 4 in the process number 0. Let us number these statement 1, 2, 3 and 4 in process number 1. Sorry, let us say we are numbering it 5, 6, 7 and 8. Fine. Now the value of A and B both are 1. Let us say P0 process executes statement number 1. P0 process executes statement number 1. With the help of the P, it reduces the value of 1 to 0. Okay? And then it preempts, the process number 1 preempts. Then process number 1 executes statement number PB. It means statement number 5. So, statement number 5 is executed by the P1 process. So, it reduces the value of B from 1 to 0. So, P is a wait operation that will decrease the value of semaphore from 1 to 0. Now, after this, let us say P0 process executes a statement number 2, this is statement. What is this statement? This is PB. So, PB checks the value of semaphore value is 0. Since the value of the semaphore is 0, it cannot further reduce this, it has to wait. So, the P0 goes to sleep, and then P1 process executes statement number 6. Statement number 6 checks the value of A, the value of A is 0. If you are dealing with the without busy waiting solution, the PA value is 0, so the P1 process also goes to sleep. So, here P0 goes to sleep, P1 goes to sleep, there is no one to wake them up, both the processes are in the deadlock. Neither the value of A will become 1 ever, nor the value of B will become 1 ever, and hence these two processes are deadlocked. So, why this has happened? Because there is a dependency of these two processes for entering into the critical section on A and B. Now, A has been set to 0 in the P0 process, and B is set to 0 in the P1 process. B is expected to be 1 in P0 process, but it is never happening because we have allowed the preemptions to take place. It means the system is in the deadlock. Now, let us see the very basic thing about the deadlock, and that is about the resource allocation graph. Whenever we are dealing with the processes and the resources and their allocations, a resource allocation graph should be built. So, the basic elements of the resource allocation graphs will be processes and the resources, and the processes and resources are represented with the help of some notations. Since this is a graph, the basic property of graph will be satisfied. This graph will contain a set of vertices and set of edges. The set of vertices are processes and resources. All these things means processes and resources will come into the same unit, and the edges means the request of a process is maintained through the edge, and the allocation of the resources is also maintained through the edge. Now, here what is happening, that we are actually partitioning the set of the vertices into two parts. The first part is set of the processes. Let us say P1, P2, Pn, this represents P1, P2 and so on so forth Pn, this represents the set of all the processes, and R set is denoting the set of resources or resource type, not the resources, resource types. So, R1, R2 and so on so forth Rm. It means we have n processes in the system and we have m resource types in the system. Now, the set of edges will be also categorized into two. One is the request edge, meaning that if a process is requesting for a resource, we will make a request edge, and when a resource is allocated to the process, we will make the assignment edge. Fine. So, these are the notations for the resource allocation graphs. The processes are represented with the circle. The name of the process is usually written inside the circle. For example, if we have a P7 process, so P7 process is represented like this. Fine. A resource is denoted by a rectangle. If we have only one dot here in the rectangle, we will say that this resource has one instance only. But in case we have 4 resource types, 4 units of this resource, then there will be 4 dots inside the rectangle, and we will say that the number of or the units of the resources available for this Rj is 4. So, the number of dots is actually representing how many units of that resource is there. Now, if we have to or PI process request for a Rj resource, then there will be edge from the process to the resource. Okay. This is the request edge. So, process Pi is requesting for some resource Rj. So, the edge will go from Pi process to Rj. Similarly, when a resource is allocated to the process, in that case the edge will go from resource to the process. The edge will go from resource to the process. Okay. So, this is the condition of, or this is showing the assignment edge. So, this was the request edge and this is the assignment edge. Based on these two, a diagram shows the allocation of the resources and the request of the resources. We can simply understand this, that P0 process is requesting for, let us say we are numbering the resource type R1, R2 and R3. So, P0 process is requesting for R1 resource, R1 resource is allocated to P0 process, R1 resource is allocated to P1 process as well, R2 resource is allocated to P1 process, R3 resource is allocated to P1 process, P1 is requesting for R1. Similarly, R2 is allocated to P3, P3 is requesting for R3, P1 is requesting for R2, P2 is requesting for R2, R2 is allocated to P2 and P2 is requesting for R2. So, the resource and processes and the request edges and the assignment edges. Now, let us say this is the resource allocation graph. It is in short known as, the resource allocation graph is in short known as the RAG. This RAG contains a cycle, if you clearly see that. Okay. In this, what is happening, that the P1 process is requesting for R1, R1 is allocated to P2, P2 is requesting for R2, R2 is allocated to P3, P3 is requesting for R3 and R3 is requesting for P2. So, P2 and P3 they fall in a circle, P2 and P3 fall in a circle, and since they are falling in a circle, definitely there is a cycle existing and we will say that the system is in the deadlock. Okay. Now, let us check a diagram where there is a cycle, but there is no deadlock. Let us say P1 is requesting for R1, R1 is allocated to P3, P3 is requesting for R2 and R2 is given to P1. So, this process P1 and P2 is in a cycle. If we separately represent this P1 and P2 processes, then P1 is requesting for a resource held by P2 and P2 is requesting for a resource held by P1. So, P1 and P2 they are in a cycle. So, since they are in a cycle, there can be deadlock, but let us see some other things as well. Since this is the model which is not the single unit model, this is the multiple unit model. So, since this is the multiple unit model, let us see that R1 is allocated to P2 and P2 has no other dependency. So, when P2 finishes, R1 will be free. So, when R1 will be free, when this R1 will be free, this R1 will be allocated to P1 and the cycle breaks, and since the cycle breaks, there cannot be a deadlock. So, whenever we can break the cycle, there will be no deadlock. Now, the conclusion is that when a RAG contains a cycle, it is not necessary that there will be a deadlock. If you are dealing with a single unit model, definitely there will be a deadlock, but if it is a multiple unit model, we will have to see other conditions as well. So, a system may be there in the deadlock, a system may not be there in the deadlock. Now, what are the methods for handling the deadlock? The very first method for handling the deadlock is the deadlock prevention, where we should take all the preventive measures such that the deadlock does not take place. Another method is the deadlock avoidance, in which we will make some conditions or we will avoid the deadlocks to take place. While allocation of the resources, we can do this. If the resources are to be allocated, let us check that if by allocating of the resources, my system may go in the deadlock or not. If it may go in the deadlock, leave that request as such. Do not allow that request that resource to be allocated to the given process. Another one may be that you let the system go freely, and whenever the deadlock will take place, handle with that deadlock. So, whenever the deadlock takes place, detect the deadlock and take the necessary action so that it is resolved. And finally, the deadlock ignorance, which is the technique used by all the modern operating systems. Even if there is a deadlock in the system, ignore that. After some times it may be resolved automatically. So, the Linux system uses this scheme, and many other systems must be using a scheme. As I already told you that all the modern operating systems use this technique for the resolution of the deadlock or dealing with the deadlock. So, as a last topic for today, let us discuss about the deadlock prevention. Deadlock prevention can take place if we can actually avoid any of these 4 conditions. If we can prevent any of the 4 conditions, we can say that the deadlock may not be there. So, the mutual exclusion cannot be prevented. If a resource is dedicated resource, we cannot change its nature to shared resource. So, handling with the mutual exclusion for prevention, not possible. Let us go to the hold and wait. Hold and wait means it is holding some resource, the process is holding some resource and requesting for the other resources. So, if a process is holding some resources and requesting for the other resources, it means that it is neither progressing or not letting other processes to progress. So, better approach would be that you take all those resources from it, and when all those other resources will be available, give it to that process. Okay? So, the hold and wait condition can be denied by either allow the process to demand all its resources required for the execution at one go, and when all those resources are available, give it to them, give it to the process. So, this scheme may allow the hold and wait condition not to take place, but it will lead to the low resource utilization, and it may also lead to the starvation for some processes. Now, the no preemption condition can be preempted by preempting a process or taking the resources back from the given process forcefully. And the circular wait, that is the last condition that to avoid. Let us allow the number on the resources. So, let us say a process has already access to the resources R1, R2 and R3. So, it cannot demand for resource R0, or let us say a process is already holding a resource, let us say R7, R6 and R5. So, it cannot demand for resource R1, R2, R3, R4. So, apply a numbering on the resource and allow the process to request for the resource only higher in number than the currently allocated. Okay? So, if R7, R6 and R5 is allocated, a process can allocate or request for R8 resource. It can request for R9, it can request for R10, but it cannot request for R1, R2, R3, R4. So, apply a numbering, logical numbering. So, this was all about the deadlock prevention. We can solve several problems. You can see these problems on the next turn. So, this is the reference for today's lecture. The 2 diagrams of the traffic has been taken from the websites given on the right hand side, and other concepts are taken from Silberscheidt and Galvin. Thank you.